Welcome to my talk. I'm Kefan Zhang from Tsinghua University, and I'm gonna talk about our paper Root and Regret for learning in Markov Decision processes with functional approximation and low gamma rank. In this paper, we focus on reinforcement learning with general functional approximation. Our algorithm is built on two assumptions: realizable functional approximation and low gamma rank. We propose this adaptive value function elimination algorithm. To the best of our knowledge, this is the first root and regret result for reinforcement learning in stochastic Markov decision processes with general value function approximation. Value function approximation means that the algorithm can access a class of Q functions that maps a state and an action to a value. The realizability assumption says that the optimal Q function is included in the class. However, there is an impossibility result. With only a value function class and a realizability assumption, no algorithm can achieve polynomial sample complexity. So some structural assumptions are needed, such as linearity of value function, block structure of transition function, or BAL Error, or low gamma rank. In this paper, we focus on the low gamma rank assumption. First, we introduce some notations. For a given value function f, we use pi f to denote the greedy policy with respect to f. In particular, the greedy policy with respect to optimal Q function is the optimal policy. Gamma error of a function f with respect to a row-in policy pi and layer h is defined by the following equation. First, we sample a state x from the distribution of states at layer h when acting policy pi. The action for layer h is chosen as a greedy action with respect to the function f. And then take the expectation of function value at state x minus single step reward and function value at next state. Look at the definition of gamma error. If we take the summation from layer 1 to layer h, then the first term and the last term will cancel out. So we have the following policy loss decomposition lemma. The difference between function value and the total reward of this greedy policy equals the summation of gamma errors. So gamma error serves as a link between function value, which is known to the algorithm, and the total reward, which is something that the algorithm wants to know. Gamma error is also closely related to gamma equations. For optimal Q function and optimal policy, the gamma error implies that a gamma equation implies that the gamma error of optimal Q function is zero for every row-in policy at every layer. On the other hand, if the gamma error is zero for any layer, then the function value equals the total reward of its greedy policy. Jiang et al. Proposed the OLIVE algorithm based on these observations. The algorithm has 4 steps. First, it will select a function with maximum value, and then estimate its gamma error with respect to the greedy policy. So if the gamma error is small, then the total reward of this greedy policy is at most epsilon less than the function value. And because of the realizability assumption, the greedy policy is near optimal. Otherwise, there exists some layer that the gamma error is large. Then the algorithm eliminates functions with large gamma error with respect to the same row-in policy at this layer. Because of the optimal Q function has zero gamma error, the elimination step will not remove the optimal Q function. When estimating the gamma error, OLIVE uses an important sampling. The row-in policy is the same for every function, but the action at layer h is different for different value function f. So the action at layer h is uniformly sampled, And actually, we can prove that the following equation is an unbiased estimation of the desiring Bellman error. In order to prove a polynomial sample complexity, it is crucial to bound the number of iterations or the number of elimination steps. This is where the low Bellman rank assumption is used. Informally speaking, we say a Markov decision process has a Bellman rank n if the Bellman error for any function f and any rho-in policy pi g can be written as the inner product of two n-dimensional vectors. The first vector depends on only g, and the second vector depends on only f. So, the elimination step given the rho-in policy ft is to eliminate functions with large inner product with the vector defined by ft. This process is similar to the ellipsoid method when solving linear program. So the number of elimination steps can be bounded approximately by the dimension of the vectors, which is the Bellman rank. So the sample complexity of Olive algorithm is polynomial in Bellman rank, number of actions, horizon, and inverse of accuracy level. But in terms of regret, an 1 over epsilon squared sample complexity only implies an n to the 2/3 regret. We illustrate this idea in the following figures. The x-axis is the number of trajectories, and the y-axis is the suboptimality of the policy. Then the red area represents the regret. Olive algorithm guarantees that after about 1 over epsilon squared trajectories, the algorithm can output an epsilon optimal policy. But before 1 over epsilon squared trajectories, the suboptimality is unbounded. For online learning, we want a gradual improvement of the performance. So the learning curve of an ideal algorithm should look like the figure in the right. That is exactly what our adaptive value function elimination algorithm does. We can guarantee that a policy with epsilon suboptimality is executed at most 1 over epsilon squared times. For example, a policy with constant suboptimality is executed at most constant times. And this is not guaranteed in the Olive algorithm. It is very possible that a policy with constant suboptimality is executed 1 over epsilon squared times, which leads to a very large regret. To achieve root n regret, we combine two techniques. The first one is doubling trick. Recall that in the second and third step of Olive algorithm, we need to estimate the Bellman error of a policy. The estimation needs 1 over epsilon squared samples, regardless of the true Bellman error. So if the Bellman error is large, the algorithm still runs the policy 1 over epsilon squared times. Our adaptive value function elimination algorithm gradually estimate the Bellman error. Every time we double the precision, so we can efficiently identify the case where the Bellman error is large. And of course, the elimination step is also done in this precision. Now, consider the estimation of Bellman error. Olive algorithm uses a uniform random action to perform important sampling. For simplicity, let us first consider the case where the horizon is 1. And the Markov Decision process becomes a bandit. In this case, it is easy to see that the suboptimality of an uniformly random action can be constant. So the important sampling step has an extremely large regret. It is of the order n. So we need a low regret, low variance approximation method, even if the state space can be infinite. And this is a contextual bandit problem. At a higher level, a contextual bandit algorithm can compute a low regret, low variance approximation of the Bellman error when the horizon is 1. So the regret of the important sampling step is bounded by root n instead of n. And for the case where the horizon is larger than 1, we can use the reward plus a function value as the reward for contextual bandit oracle. Now the regret comes from 3 parts. The first part is the regret of a row-in policy. This is low because the elimination step is done at the level of epsilon I. The second part is the suboptimality of importance sampling policy. This part is bounded if we use the contextual bandit oracle correctly. The third part is the prediction error. This part comes from the fact that we only use the function value as a surrogate reward for the contextual bandit oracle. And the true reward when executing the policy might not be as large as the function value. But the form of this error is very much like the policy decomposition lemma. So we can use the lemma again. The prediction error equals the expected Bellman error with respect to a concatenated row-in policy. If the expected prediction error is large, we can identify a function g such that the Bellman error of g is large. This step is done by binary search over the support of the distribution computed by contextual bandit oracle. Then we can recursively call the elimination step starting from layer ht+1. Note that the parameter ht of the elimination step is monotonic, so the elimination step eventually terminates. In conclusion, the expected regret of our adaptive value function elimination algorithm is root n for n trajectories. The AVE can be extended to the case where the function class is infinite, but has a finite statistical dimension. We also want to point out that the computational complexity of this algorithm is not polynomial. In fact, even the elimination step in Olive algorithm is proved to be NP-complete. Thanks for listening. If you are interested, please see our paper online. Any questions are welcome.